So this is the first lesson in a unit where we're really focusing on derivatives, and this unit and the next are all about derivatives. This unit's about first elaborating more on what a derivative is and understanding, what a derivative represents. But most of this unit is really going to be about how to actually find the derivatives of pretty much anything, any function or relation, and becomes quite algebraic after a while. And then the algebraic work can become quite intense sometimes. The next unit is focused on using derivatives and applications of derivatives. So with that said, let's go back to something that should be familiar. That's the definition of the derivative. And the derivative of a function is denoted with f prime, and it is, again, defined as a limit that you see here. All right, that said, there's actually a whole bunch of different ways of expressing a derivative, and historically it comes back to the fact that the fundamentals of calculus were sort of developed at the same time by two different people in two different countries, and over years they've kind of developed separately, and so there's, just long story short, a whole bunch of ways of saying the same thing. And so everything you see here represents the same thing. These all represent the derivative of some functions. F prime, which you've seen before. This next one, we say d dx of f of x. And again, you can kind of get a sense of how this comes back to the slope. You can see this sort of fraction there. But d dx f of x is how we say it. And again, just represents the derivative. In this case, you can kind of think of the derivative as an operation applied to a function. This d dx is being applied to f of x. But again, everything you see here is equivalent. Next right here, dy dx makes a sort of connection to slope even more direct. And just that, dy dx, is another way of describing the derivative. And you can kind of, again, makes it really clear that a derivative is a rate of change. You can kind of think of it as a change in y over change in x. And this last one, y prime, is very similar to f prime, just not in function notation. And again, this is something that we'll use later when we deal with implicit differentiation. But again, everything you see here is equivalent. You need to understand these all just represent the derivative of some function. Okay, that said, we can also deal with second derivatives and third derivatives and the derivative of the derivative. And without going too much into it, for each of these types of notation up above, what you see down below is how we denote the second derivative, which again means the derivative of the derivative. Or in terms of slope, it's the slope of the slope function. Either way, regardless if that sounds confusing or not, these all represent the same thing. And so if you have f double prime means the second derivative. If you have this symbol twice, which can also be written like this, again means the second derivative. You can literally, on the left, you can see the same operation is applied twice. And then all these represent the same thing. And depending on what the function represents, the second derivative can be very important or it can be meaningless. It depends on what f of x represents. And I don't want to say too much right now, but mostly starting with notation. With that said, the majority of this lesson right here is about developing a feeling for how the graph of a function would relate to the graph of its derivative. Because if you can find the derivative of a function, then you should be able to graph that derivative. And there should be relations between the graph of a function and its derivative. And so let's look at this. I have a graph of f of x. And it looks kind of like a part of a wave. Well, it is a type of wave, but it's actually not a sinusoidal function, but it's similar. That's it. Who really cares? Here's the function. And I should say that there are endpoints. These are meant to be endpoints. Here and here. OK, so first I'm going to look at this graph, which again is f of x. And I want to fill out this table, which notice its values of x and f prime of x. So for each of these, f prime represents the derivative at that point. So for the first one, I want to find the derivative, or estimate the derivative when x is negative 5. And what does that mean again? When x is negative 5, I want to visualize what the tangent line would look like at that point. So I'm going to get a nice skinny line here. And the tangent line right at negative 5, estimating, would look something like this. That's my estimation of what the tangent line looks like at that point. And so now the derivative at negative 5 is the slope of this line. And if I drew a perfect tangent line, it would be exactly the slope as this. I'm not going to be so bold to say this is perfect, but I think it's pretty good. And looking at this line, if I compare this point to this point, I see a slope of up 4 over 1. So the slope at that point seems to be 4. All right, so same idea. And at this point, maybe I'll do one more, and then I'd highly encourage you just to try the rest of this on your own. But I'll do one more. Let's look at when x is -4. So for that, -4 is right here. I want to look at this point right here. I want to visualize a tangent line at -4, something like this. Again, I'm not going to say that's perfect, but I think it's pretty good. It's definitely not a terrible tangent line. And looking at that line, looking at 2 points of it, that seems to have a slope of 2, up 2 over 1. So what I'd highly recommend at this point is that you pause the video and try the same thing for the remainder of these points. All right, so I hope you've already tried this. So next, when x is -3, that's right here. And that's, I'm hoping, a fairly easy tangent line to draw because it's just horizontal. At that point, the line is not going up or down. That's the instant it changes from increasing to decreasing. And so that tangent line I drew is horizontal, so the slope is 0. And notice I do see a pattern here. I don't want to jump to a conclusion too much, but if you look at my derivative so far, I have 4, 2, 0, so perhaps the next one will be -2. That said, let me look at -2 right here. And so the slope at that point -2 looks like a pretty good slope for that. And so let's see if the next one ends up having a slope that looks like around -4. So I'm looking right here. And yeah, a slope of -4 for the tangent line looks about right. So now let's see if the next one's -6. And it won't be. But like I said, we don't want to jump to a conclusion too quickly about things. But if I look at when x is 0, so right here, the tangent line here seems to be, the slope of that tangent line seems to be more like -2. So my pattern's changing now. And I will say later on in the course we'll realize that that's because this point here is what we call an inflection point. That's it. I don't want to get too far ahead of myself, but that's why the pattern of this derivative has changed now. It's no longer, it's now going back up, it seems to be. And so I can see, looking at when x is 1, I have another horizontal line for my tangent. So the slope of that is 0, and 2 left. So at 2, the slope seems to be about 2. And then at 3, the slope is going to be about 4 again. Or I really should say the slope of the tangent line is about 4. So notice I drew all these tangent lines and estimated the slope. And so I had here 2 and 4. All right, so I'd have here is a table which I estimated. I mean, to be honest, I can't be too certain about the exact values for these derivatives at different points, but they should be pretty good. And to be honest, I made this question, so I actually know what the slopes are, and these are actually correct. But that said, I should never get too certain that these have to be perfect. But now I have a table for x and f prime of x, which means I should be able to make a sketch of what f prime of x looks like by first plotting out these points on a table. And I have a lot of them, so I'll show this in red here. And so, -5, 4. So what I'm plotting here is the derivative. And then -4, 2, -3, 0. Oh, it helps if I can count here, put those points in the wrong spots. And then this is where my slope starts to go back up. So at 0, it's -2. And so these are just by plotting the points. And so I can feel pretty confident that it probably looks like this. Now a few things. I should not draw arrows on this function because if you look at function f, I said it had endpoints at -5 and 4. Sorry, -5 and 3, which means my derivative should not go beyond -5 and 3, because after that the function doesn't exist. And remember, what I just sketched out here represents the slope of function f at any given point. And so if function f is not defined, there can't be a slope at that point. As well, though, notice this looks like an absolute value function, and that is because what I actually have here is this is actually x squared, a variation of x squared, and this is another variation of x squared. And so because of the specifics of how I made f of x, that's why I'm getting this absolute value function. But please, while there's a reason for why this looks like an absolute value function, please now don't think that everything's going to look like an absolute value function. What I have here, notice, is again a graph of f of x and the derivative. So a few things I'd like to notice before we try a more complex example is, notice if I look right here, that I'm highlighting in yellow. Actually, I'll pick a different. Yeah, we'll go with yellow. If you look in this region here and this region here, this is where f of x is increasing. If you look from left to right, this is where the function is going up. And those same intervals, that's where my derivative is above the x-axis, the exact same intervals. And that's not a coincidence, because when your function is increasing, that means the slope is positive. And the slope is positive, the output of the derivative is a positive number. And if I look right here in this interval, that's where my function was decreasing. And notice that exact same interval, that's where my derivative was below the x-axis. As well, notice right here and right here, that's where my function had vertices. That's where it was neither increasing nor decreasing. And notice that's where I have x-intercepts on my derivative. None of these things are coincidences. And then, these are things we'll see a lot and work with a lot. But if you understand slope, how a positive slope of function is going up, which means the derivative must be a positive value, and a negative slope, the derivative must be a negative value. All right, so with that said, I have one more example of this weirder looking function that I'm calling g of x. And again, I would highly recommend that in a moment you pause this video to try to do essentially the exact same thing on your own. It's harder, so you'll surely make a few mistakes unless you've done this sort of stuff before, but it's far more valuable to try this on your own before I just do it all for you. Okay, so please pause the video, try the same thing, and then I'll work through all this. All right, so I got a bunch of tangent lines that I want to estimate the slopes of. So for this, well, first of all, in the first part, when x is -4, or when x is -1, or when x is 1, all those points there, sorry, it helps if I can count. There is no, when x is -4 and -1, sorry. I, for some reason, colored in -2. At those points there, the first 2 points of my table, the slope is quite easy to see. I don't even have to draw a tangent line because my function is a line at that point. There's a linear segment there. So I can just see that line has a slope of 2, which means I know the derivative at these 2 points must be 2. Okay, next at 0, right here. What's the tangent line at this point? Well, honestly, it's not possible to draw a tangent line at this point. I mean, if I look from the left, the tangent line looks like this line. If I look from the right, it looks horizontal. So how can I put those two together? I can't. It's not possible to draw a tangent line at 0. And so at 0, the derivative, it does not exist. Remember, a derivative is a limit. And so limit does not exist at that point. You can kind of think about the limit from the left and the right not agreeing. At 1, I'm looking right here now. So here, at 1, I can draw a tangent line at that point.
Addison Ham, please come to the office. Addison Ham, please come to the office.
Right at that point, at that instant, the tangent line would still be 0, because from the left, it's a horizontal line. From the right, it looks like a quadratic function that's leveling off at a vertex. And so still from the left and the right, the slope is approaching 0, and so the derivative at 1 would still be 0. Looking at when x is 1. So when x is 2. I'm not very good at counting today. So here I need to kind of visualize this and estimate. Really, until now, I haven't really had to estimate at all. But my quick little sketch looks something like this. That's my sketch of a tangent line. Looks about -2. When x is 3, I'm looking right here. Again, I can't actually draw a tangent line there. From the left, it looks like this. From the right, it maybe looks something more like this. Those aren't the same. There's no way I can draw a tangent line at that point. So again, when x is 3, my derivative does not exist. Okay, what when x is 4? Well, I can draw a tangent line there. Maybe something like that. And looking at the tangent line, it looks like a slope of, it's definitely negative, negative a half or so. When x is 5, I don't need to draw the tangent line. I can see right there the slope is going to be 0. It's neither increasing nor decreasing. At 6, I got to estimate this again. And something like that. Looks pretty much the same as the slope was at 4, just going up, so I'll say positive 1/2. 6.99, really, really close to 7. So, roughly, like, I don't know, right there. If I look there, I mean, this looks like a semicircle, and that is actually part of a circle. Right there, though, regardless, this is really, really steep. I know it's not quite vertical at that point, but it's really, really, really steep. So the slope at that point is a really, really large number. Remember, the larger the number, the steeper the slope. And while this is not perfectly vertical, it's very, very close to being vertical. So all I'll say is I don't feel comfortable putting a number down, but I'll just say it's a big number. And honestly, it sounds kind of strange, but I'm trying to do all this to visualize a graph in a moment. All I know is it's a very big positive number. Really, it's too steep for me to even pick 2 points. That's it. Right at 7, at that instant, right at 7, my tangent line would actually be straight up and down. It's kind of the opposite of my tangent line at 5, whereas that was horizontal. And a perfectly vertical line is a slope that's undefined. So again, my limit does not exist. However, I know the closer I get to 7, the bigger my slope gets. So I'll make a little note here. So even though at 7 itself the slope is vertical and a vertical slope is not defined, I know as x approaches 7, f prime, or actually I should say g prime, is approaching positive infinity. Keeps getting larger and larger and larger. So let's put all this together. What does this derivative look like? And again, at this point, if you have not actually tried sketching out the graph, I would pause the video. But let me start visualizing this graph. Okay, the easiest part is where I'm dealing with line segments, because the slope of a line doesn't change. So the derivative is a constant at that point. And so from -5 to 0, my slope is just 2. That's it. At -5, I'm okay. Or -4, sorry, I should say. I'm okay. At 0, my derivative did not exist. So that's why I put an open point there. And then if I look from the left, the derivative was 2. If I look from the right, the derivative is 0. So my derivative is going to jump down to here.
Addison Ham, please come to the office. Addison Ham, please come to the office.
So I have an instant change in the slope, which you can just see from the graph, which means my derivative has an instantaneous change, in this case from 2 down to 0. It's still not defined at 0, hence I have 2 open points, but my slope instantly changed, my derivative instantly changed. That's it. From 0 to 1, the slope is 0. And then it starts to go into the negatives. So what do I know? Well, I plotted, if I look here at 2, I have -2. But by the time I get to 3, the slope does not exist again. So I'm going to draw something kind of going down. But what about right at 3? The slope did not exist, but if I look from the left, it does seem to be approaching, I don't know, what's the slope of that line there? -3, -4, I know it seems to be going down, but right at, I don't know how far down. I know the slope keeps getting more and more steep until we get right to -3. At -3, again, the slope of the tangent line does not exist because I can't draw a tangent line. But as I get closer from the left at 3, the slope is still getting steeper. That looks like a parabola is kind of getting steeper and steeper. But right at 3, I have this kink in the graph. And so from the left, it looks like I'm estimating around -4. On the right, if I look from this way, I don't know what the slope of the tangent line is at this point, but it's still going down, so it's a negative number, but not as steep as it was over here. So I know the derivative as I approach 3 from the right is still a negative number, but not as negative as when I approach from the left. So I'm going to estimate, I don't know, around negative, I don't really care, negative here, okay? But I do know by the time I get to 5, the slope is 0. And notice as well, what I estimated at 4 right here, the slope was -1/2. So something like that. And again, how far down that point is, I don't know. How far up that point is, I don't know. I just know that they're both negative, and I know this point is farther down. Because I know, just by looking at the graph, from the left, the slope of this function is steeper than that point from the right. Again, a lot of stuff to look at here. Let me just erase some of these arrows now. Lastly, though, what's left? This last little section. So what's happening now? From 5 to 7, the slope starts going back up. And by the time, the closer we get to 7, the larger it gets. And I know at 6.99, it's a really, really big number. But at 7, it does not exist because the slope is vertical. But I also know, like I stated right here, the closer we get to 7, the closer, the slope, the derivative approaches infinity. Which means there must be an asymptote, a vertical asymptote, at this point. So right at 7, my derivative is undefined. We knew that already. Once we realize that the tangent line right at 7 is a vertical line, and that's because I really have part of a circle right here. And that side of a circle, their tangent would be vertical, and the slope of a vertical line is undefined. So I know there's a vertical asymptote there. But I also know as the closer I get to it, the larger my slope gets, which means the larger my derivative gets. So I guess I can estimate a bit more. I said 6, the slope was about 1/2. I have that on my table, so about here. But then it has to quickly approach and go up. And so what I have here is my graph, my sketch of g prime of x. Notice there's various discontinuities. There's a jump discontinuity. There's 2 jump discontinuities. There's an infinite discontinuity. There's a lot of stuff going on, and that's difficult. And please don't think I expect you to be able to, sketch this with ease anytime, really, really quickly. But it is an expectation that we can sketch these things. And really, it all comes down to visualizing how the slope is changing. And sometimes it's fairly straightforward, especially with linear segments. Sometimes it's not straightforward at all. All right, but that's where I'm going to stop this lesson.